Okay, welcome everybody. We're going to work through the Unit 4 practice exam here, starting with this first problem here. All right, let's get started. So Mackenzie walks directly toward a plane mirror at the speed of 0.3 meters per second. Determine the speed of the image relative to her. Okay, so, well, first of all, I like how the writers of this problem got personal and gave the person a name. Secondly, the important thing is that we know relative to her. So if we have, here she is walking towards the plane mirror, so she has some velocity. Her image is on the other side at an equal distance. Remember that d object equals d image for a plane mirror. So if she is walking at the speed, then her image is coming back at the same speed. So relative to her, she's going to see 2v, because she's moving towards the image, and the image is moving to her, towards her at the same speed. So her the velocity of the image will be 0.6 meters per second. It's option C. Okay, on this next one, it's just a little geometry. You've got two mirrors arranged shown in the drawing. Light is incident from the right on the first two mirrors at an angle of 70 degrees. The light reflects towards the second mirror, reflected angle theta. Determine the angle theta. Well, you know the angle of incidence always equals the angle of reflection, so this will be 70 degrees. All right. Let's see. So this and this is a right angle. So if this is 70 degrees, this is 20 degrees here. This angle must be 135 because 45 plus 135 equals 180. Okay, so now we're going. So if this is 135 and this is 20, so that's 155. So that means the angle over here has to add up to 180. Because the three angles of a triangle add up to 180, so that means it must be 25. This and that add up to 90 degrees, so this must be 65 degrees, 65, 70, 80, 90, 90 degrees. So that means this has to equal, the angle of incidence has to equal the angle of reflection, so this equals 65 degrees. An object is placed 1 meter in front of the mirror. An observer stands 3 meters behind the object. For what distance must the observer focus his eyes in order to see the image of the object? So this is the mirror. Here is the object 1 meter away from the mirror. Here is the person 3 meters behind the object. Okay, 3 meters. So that means it is 4 meters from the person to the mirror. Now we know with a plane mirror, it's always going to create a virtual image on the other side of the mirror, equal distance to the distance of the object itself. So that means the distance from the person to the virtual image is 4 plus 1, that is 5 meters. Okay, question 4. The focal length of a spherical concave mirror is 25 centimeters. What is its radius of curvature? Well, if it's concave, we know the focal length is equal to 1/2 the radius of curvature. So the radius of curvature must be 2 times the focal length. 2 times 25 centimeters equals 50 centimeters. So you've got a convex mirror in an amusement park. I'm just going to draw a sketch. Convex will look like this. The radius of curvature is 3 meters. A man stands in front of the mirror so that the image is half as tall as its actual height. So the height of the image equals 1/2 the height of the object, which is the guy. At what distance must the man focus his eyes in order to see his image? So what we want to find is the image distance, which is the distance to the guy, plus the distance the object distance, which is the distance between the guy and the mirror, and the image distance, which is from the image to the mirror. Okay, so there's a guy here, standing here. Oh, I'm sorry. This is a convex, not concave. Which makes the problem simpler because you know that the image is going to be on the other side of the mirror. So you want to find d0 plus di. So then, where to start? Well, you're going to have to use the mirror equation, and we know that the focal distance is equal to negative 1/2 r, because it's a virtual image, so it's negative 1/2. The focal length is equal to negative 1/2 the radius of curvature. Also, we don't know anything else. We don't have any other unknowns here, but we can put, let's say, di in terms of d0. So let's look at the magnification. That's the other equation to work with. That's the height of the image over the height of the object, and we also know that equals negative di over d0. Well, the height of the image over the height of the person, let's see. This is 1/2 h0 over h0 equals negative di over d0. These cancel out, so I can say d0 is equal to negative 2 the image. That can then go in here. d0 is negative 2 di plus 1 over di equals 1 over negative 1/2 r. Well, I can multiply this fraction by negative 2 over negative 2, so I have 1 over negative 2 di plus negative 2 over negative 2 di. So all I did was multiply this by 1, equals, I'm going to flip this, negative 2 over r. That makes it a little cleaner. So 1 minus 2 is negative 1 over negative 2 di, the common denominator, equals negative 2 over r. These negatives cancel. I'm looking for 2 di, so let's see. R equals negative 2 times 2, negative 4 di. Or di equals r over negative 4, which equals 3.00 meters, oops, excuse me, over negative 4, which is negative 0.75 meters. So we have one thing, and since we also know that d0 is equal to negative 2 di, we can plug in this, and we know that the object distance is positive 1.50 meters. So d0 plus di is equal to 1.50 meters minus 0.75 meters. Actually, I'm going to have to add a little constraint here. I'm going to have to say the absolute value. Why? Because this is like a number line where this is positive and this is the negative direction. And we know that the image is back here, so we're going to have to add the magnitude of d0 plus the magnitude of di. So that will get rid of this negative sign, and the answer is going to be 2.25 meters. That's the tricky part here. I should have gone up here. We don't want just do plus di. We want the absolute value of each. A spherical concave mirror of radius of curvature, I'm going to go ahead and write the knowns here, 6.0 centimeters. At what distance from the mirror should a 6 centimeter object be placed? Okay, so the height of the object is 6.0 centimeters to obtain an image that is 48 centimeters tall. So the image is 48 centimeters tall. Okay, and we're looking for what distance from the mirror, so that's what we're looking for. This one, the correct answer when I solve it is not here. I think there's a mistake on this question. so be aware of that. These last two questions are also pretty long and time consuming. You might expect maybe one of these on the test, definitely not two of them. Okay, so let's start working that. So this is we're gonna work this in the same way. I'll move it here. We'll first get DI in terms of D naught, the image distance in terms of the object distance. So let's use the magnification equation. So the height of the object over the height of the, the height of the image over the height of the object. And we also know that is equal to the negative of the distance to the image over the distance to the object. So that means DI equals negative DO times HI over H naught. And since this gets a little messy, I'm going to throw in the numbers already and say this is negative HI 48 centimeters over 6.0 centimeters D naught, or DI just equals negative 8 D naught. Okay, so let's go back to the mirror equation. Okay, and 1 over F, again, that is, in this case, this is a concave mirror. Okay, so with a concave mirror, the focal length is equal to 1/2 the radius of curvature. If it were a convex, it would be negative 1/2 the radius of curvature. For F, it's going to be 1 over 1/2 R, right? That's positive 1/2 because it's a concave mirror. I can now insert in for the image distance, let's see, 1 over D naught plus 1 over 8, negative 8 D naught equals, I'll simplify this a little bit, 2 over R. So let's combine this. I'll need to multiply this side by 8 over 8, so this term anyway, so it's just multiplying by 1. So 8 over 8 D naught plus, I'll put a negative 1 over here, over 8 D naught. I just moved the negative into the numerator, just playing around with it, equals 2R. So now I have like denominator, so that's going to be 7 over 8 D naught equals 2 over R. And let's solve for D naught. So 7R equals 16 D naught. D naught equals 7 over 16R equals 7 over 16 times R, which is, what is R again? 6 centimeters. So notice that's not one of your options. I think the problem is messed up here. The answer should be 2.63. The table lists the index of refraction for various substances at 20 degrees Celsius for light with a wavelength of 589 nanometers and vacuum through which substance will light with a vacuum wavelength of 589 travel with this rate of speed. Well, the index of refraction is C over V. I always think of it this way. I know C has to be on top because it's greater than 1. That's the way I remember that. So the velocity is equal to C over N. So as N gets large, velocity gets small, and vice versa. If we're looking for the greatest speed, we're looking for the smallest index of refraction. So the smallest here is ethyl alcohol. So that's going to be C. 8. When certain light rays pass from vacuum into a block of unknown material, the measured index of refraction of the material is 3.00. What is the speed of light inside the block? It's the same kind of thing. It equals C over V, so V equals C over N. And we have the index of refraction. The speed of light is 3.00 times 10 to the 8th meters per second. And the index is 3.00, so the velocity then is just equal to 1.00 times 10 to the 8th meters per second. C. All right, a ray of light is propagates in water and strikes a sheet of crown glass. If the angle of refraction in the glass is that, determine the angle of incidence. Okay. So this is theta 1, N1, and this is theta 2, N2. Make sure you get the right angles. You're looking for the angle with respect to the normal. A 0-degree angle means it comes in perpendicular to the surface. Determine the angle of incidence. So that's theta 1. N1 sine theta 1 equals N2 sine theta 2. So theta 1 is going to be the inverse sine of N2 over N1 sine theta 2. So theta 1 is equal to the inverse sine of N2. That's N2 and this is N1. 1.333 sine of 35.2 degrees, which is theta 2. When you put that in your calculator, let's see, you get 41.1 degrees. So that's a little close to 41.2. Okay, so complete this following statement. Fiber optics make use of total internal reflection. That's because the light is totally reflected along the boundaries of the fiber optic, and that's what keeps the light in there. Polarization, chromatic aberration, none of this stuff matters. Okay, so light rays traveling in a diamond. If the ray approaches the diamond air interface with the minimum angle of incidence, that will result in all of the light reflected back into the diamond. That is the critical angle, the angle for total internal reflection. So I'll go ahead and label as such the critical angle. This is N1 equals 2.419 and N2 equals 1.00. So the equation for the critical angle is sine of theta N2 over N1. Or the critical angle equals inverse sine of N2 over N1. And you punch that in your calculator, you get that the critical angle is equal to 24.4 degrees. Okay, we now have a ray of light in oil incident at the Brewster's angle upon a flat surface of quartz crystal. Determine the angle of incidence for this ray. Well, that is the Brewster angle, where N1 is equal to 1.21, N2 is equal to 1.458. Okay. So the equation for the Brewster angle is tangent of the Brewster's angle is equal to N2 over N1. So that means the Brewster angle is equal to inverse tangent of N2 over N1. .458 over 1.21. That equals 50.3 degrees. You know, something I should note here is that with the total internal reflection, I don't know if I made a big deal of this in class or not, but N2 must be greater than N1. Excuse me, the N1 So something to point out here is that N1 must be greater than N2 when we talk about total internal reflection. And that's the case you have here. N1 is greater than N2. So for light going into water, for example, there will never be an angle at which is totally reflected in the air. Some of it will always penetrate just because this condition is not met. It must be, the argument of the inverse sine must be less than 1. And that makes sense because sine of theta equals opposite over hypotenuse. Well, the hypotenuse must be bigger than the opposite side of the triangle, or it's not a triangle. All right, so that's a condition set on total internal reflection. Something to remember. All right, for this next part, you're asking about air that comes into glass and then travels in a straight line into the unknown liquid. In order for this to happen, the index of the refraction of the unknown liquid must be the same as that of the glass, so there's no refraction here. It goes from one straight through to the other. Next one, which the following statements is true concerning the focal length of a lens. The focal length is not the same for all colors. It is different for colors, but not because of reflection, and is different for colors because of dispersion. Yes, that is what we call the way you have an index of refraction for each specific wavelength of light. Polarization and spherical aberration are different stuff. So a converging lens here in 15 is used to focus light from a small bulb onto a book. The lens has a focal length, I'll write this down, 10 centimeters, and is located 40 centimeters from the book. So object distance is 40. Determine the distance from the lens to the light bulb image. That's what we're looking for. Okay, so we have this situation. Here's the light bulb. Here's the lens. Image distance is 40.0 centimeters. And we want to find the, the object distance is 40 centimeters. We want to find the image distance. Well, this one's pretty simple. For d naught plus 1 over di. We have the focal length, we have the object distance, we just need to find the image distance. So that is equal to 1 over f minus 1 over d naught, and the inverse of all that, 1 over 10 centimeters minus 1 over 40 centimeters, the inverse of that. And that's going to equal 13.3 centimeters. Okay, last one. Object has a height of the object is 4 centimeters. It's placed at distance 30 centimeters from the lens. The inverted image has a height of negative 1.5 centimeters. Why did I put the negative in there? Because it said the inverted image. So what is the focal length of the lens? Well, just like before, I'm going to use the magnification equation to put, the image distance in terms of the object distance. So the height of the image over height of the object equals negative distance to the image over distance to the object. So that means di is equal to negative d naught hi over h naught, which equals negative 30 centimeters over negative 1.5 centimeters over 4.0 centimeters, or the image distance is equal to 11.3 centimeters. So now when I take my Finland's equation, then I can say, I'll make that into an arrow, the focal distance, focal length, is equal to 1 over d naught plus 1 over di, the inverse of that, or 1 over 30 centimeters plus 1 over what I just found, 11.3 centimeters. Punch that in your calculator, you get 8.2 centimeters. Okay, the real test will be much shorter, about 12 problems. I have consolidated several of the problems, so you'll see, like, one scenario with light on an interface and tell me everything about it. Tell me Brewster's angle, tell me critical angle, tell me angle of refraction, and so on. So that it should go much faster than this. And this had a lot of the more complicated problems like this that you'll maybe see one on the test. All right.